Hi, I'm Tom Reader, and I'm going to tell you about p-values with the help of this bag of chocolates. Oh, that was a raisin. Bad luck, I suppose. I love these chocolates, but not all of them. There are 3 flavours: peanut, raisin and solid chocolate. I love the peanuts and the solid ones, but frankly, I think the raisins are disgusting. The problem is you can't really tell the difference, so every time you reach into the bag, you're risking disaster. Oh, bother. Raisin again. Double bad luck. Oh well, best just dive back in. Raisin again? Come on, so unfair. What's going on here? If I had a suspicious mind, I would start to think that somebody had tampered with my chocolates. But I'm not like that. I know that bad luck just happens, right? This time, it will be a good one. That's it. I've had enough with this. I reckon somebody's deliberately tampered with these. I did leave them lying around while I was giving that stats lecture. Perhaps someone swapped all the nice ones for raisins. Or maybe I'm just having a really unlucky day. So this kind of thing happens to people, and especially to researchers, all the time. You collect some data, in my case the flavours of some chocolates, and you spot a pattern. You ask yourself, does that mean something, or is it just the result of random chance? Did I get 5 horrible chocolates in a row because I'm unlucky, or is there something more sinister going on? I could go on gut instinct, but surely there's a more objective way of deciding what's going on. What we need is a way of quantifying the chance that the pattern I've seen is just a coincidence, just the result of random events. If we know that a pattern is extremely unlikely to be a chance event, then that tells us something else is probably causing the pattern, and that's when, as researchers, we tend to get particularly excited. So what is the chance of getting 5 rubbish chocolates in a row? If it's just an ordinary bag of chocolates, well, how do we calculate the chance? That depends on our null hypothesis. In other words, it depends on what we consider ordinary to be. My chocolates here normally come in 3 flavours, only one of which I don't like. And because we don't know any better, let's just assume that all 3 types are equally common and that each bag contains a random mix. That effectively is my null hypothesis. So if I dip into a normal bag of chocolates, which hasn't been tampered with, the chance of me getting a raisin should be 1 in 3, or 1/3, or 33%. Statisticians might say that the probability of getting a raisin by chance under the null hypothesis is 1/3. Okay, but what if I get 2 raisins in a row? What are the chances of that happening if the bag is just a normal bag of chocolates? Well, that's 1/3 times 1/3, which is 1/9, or about 11%. That means if I pulled 2 chocolates out of a bag 100 times, I should get a pair of raisins about 11 times, and the other 89 times I should get at least 1 nice chocolate. Okay, so in the real world, if you get 2 raisins in a row, you'd probably not be too freaked out. And that's because you have a pretty good intuition for the fact that it's fairly likely to happen by chance, 11.11% to be precise. So what are these probabilities I'm talking about? There was the 33% chance of getting 1 raisin, and then the 11% chance of getting 2 in a row. These values are what we call p-values. P stands for probability, and specifically in this case we mean the probability of observing a particular pattern in your data by chance if the null hypothesis is true. In other words, if nothing strange or interesting is going on normally from a scientist's point of view. Okay, so what if you get 5 horrible raisins in a row? Well, the chances of that happening under the null hypothesis are much lower. 1/3 times 1/3 times 1/3 times 1/3 times 1/3 is about 0.004, or 0.4%. So P is 0.04, and that's less than a 1 in 100 chance of the event happening just by chance if the null hypothesis is true. So yes, it could happen, but it's a pretty rare event. In fact, the pattern we've observed is so unlikely to arise by chance that we might conclude that the null hypothesis is probably wrong, and therefore that the chocolates are probably not normal chocolates. If it's not random chance, the pattern we've observed must indicate something else is going on. We need an alternative hypothesis. In my case, a possible explanation is that someone's tampered with my chocolates. Maybe they've swapped all the nice ones for raisins, or simply eaten all the nice ones and left the raisins behind. Or maybe some problem with the manufacturing process happened and we've ended up with a bag full of only raisins. It doesn't really matter. Lots of possibilities. Okay, so how is all this chocolate stuff and probability relevant to the real world and to real research? Well, in all subject areas, we want to be as objective as possible in the conclusions we reach from the patterns that we observe. So if I'm trying to decide if a new drug is curing my patients of a disease, I need to know how likely it is that the patients I've treated would get better anyway, just by chance. Would you really want us to spend all that money giving an expensive drug to people if it turned out that the positive effects that I had observed previously were simply the result of random chance? What about if I want to know if the government's new policy to give everyone free chocolate is improving happiness levels? I might survey a randomly selected group of people before the policy was introduced, and then another group afterwards. I need to consider how likely it is that the second sample of people I surveyed just happened to be of a sunnier underlying disposition. All that talk of chocolate reminds me